All right, section 7.9, gases in chemical reactions. This is kind of rolling some things together from previous chapters. You'll be able to predict how the pressure in a fixed volume container will change after a completed reaction. So key there is that we have a fixed volume container, and what we're looking at is a change in pressure. Okay. So stoichiometry and gas laws. The ideal gas law can be used to calculate the number of moles of a reactant or product gas, which then can then be used in stoichiometric calculations to determine the mass of a reactant or product. Okay, the stoichiometric calculations can provide the number of moles of a reactant or product gas, which can then be used in the ideal gas law to calculate the pressure, volume, or temperature of that gas. Now, here what we've got is this somewhat complicated flow chart that shows us relationships. So essentially at the heart or at the center of it, we've got a balanced chemical reaction, and that will allow us to look at the reaction of A going to B and in reverse as well. So you can, once you have that balanced chemical reaction, then you can figure out the mass of reactant A or the volume of A. How do you do that? By looking at the molar mass and molarity. You can also figure out the moles of element A in this sort of question. You can also relate that to, or with the ideal gas equation, the pressure, volume, and temperature of A. And so this is just kind of this is almost like your thought process will include all of these steps when you're solving these sorts of problems. So let's see this sort of thing in action. What we have here is how many liters of oxygen at 21 degrees Celsius. I'm going to take that temperature and I'm going to convert it to degrees Kelvin, so 294.15 Kelvin. Your pressure is 1.13 atmospheres. Can be prepared by the thermal decomposition of 0.950 grams of KClO3. Okay, so how many liters of O2 gas? Okay, oxygen, O2 gas, that's what we're concerned with. And we are looking at the volume of, or I'm going to say VO2 of this. So essentially what we have here is a balanced chemical reaction where we have our mass of our reactant, KClO3, and we have a product that we're kind of that we're concerned with and that we're most curious about. Okay, so when we look at the ideal gas equation, PV equals nRT, essentially, what do we need? Okay, so temperature is accounted for, pressure is accounted for, volume is what we don't know, but what we want to do is look at, well, moles of KClO3 and relate that to our moles of O2, okay? Because that will allow us to solve for that N value, okay? Now, what I want to do is I want to figure out 0.950 grams of KClO3. And what is my molar mass of KClO3? So looking at the periodic table, I can see that potassium has a mass of 39. I'm going to call it 39.1. Cl is 35.5. O3 is going to be 16 times 3 is 48. So KClO3 has a molar mass of 122.6 grams of KClO3. That's 1 mole KClO3. So 0.950 divided by 122.6 is 7.74 times 10 to the minus third moles of KClO3. All right, now effectively that gives us our number of moles of O2 that we need to solve for, or that we need in order to solve this sort of problem. And how does it do that? Well, it does that because of the fact that we have a molar ratio of 2 moles of KClO3 to 3 moles of O2. And so what we're going to do is I'm going to take this equation and I'm going to kind of extend it. So 0.950 G KClO3, and I'm just rewriting this because I want to illustrate this concept completely. 122.6 grams of KClO3 is 1 mole KClO3. And then my balanced chemical reaction tells me 2 moles KClO3 and 3 moles of O2 is going to give me my number of moles of O2. So 0.950 times 3 divided by, parentheses, 122.6 times 2, close parentheses, equals 0.0116 moles of O2. So once I have that, well, it's really just plugging it into the rearranged ideal gas equation. V is equal to nRT divided by my pressure. So V is equal to 0.0116, 0.08206. My temperature is going to be 294.15 divided by my pressure, which is 1.13. So I've got 0.0116 times 0.08206 times 294.15 divided by 1.13. And I get my volume of 0.248 liters. And that's all there is to that sort of problem. All right, I hope this is helpful, and we'll proceed onward.